Okay, kids, time for some math. It's physics. You know it. Equation coming up. All right, well, we got an equation for. Well, we just went through induced EMF. In other words, voltage, which is going to push electrons and create a current. What we want to know is how much voltage can we generate, and therefore how much pushing potential can we then. And then, therefore, if we know the pushing potential, we remember V is I times R, and power is V times I. We can then calculate the amount of current we can generate. So we need to figure out how much voltage that we can get. That's where Mr. Faraday, a.k.a. the cotton candy guy, Faraday, that's where he comes in. Faraday's law, this is a law. This is actually a real law, too. This one is actually like all the time happens kind of a law, not like the suggestion of Ohm's law. Ohm's law. Yeah. This is Michael Faraday's induction law. Here it is. Mathematical, kids. Equation time. So EMF. And EMF means voltage. Okay. All right, that's what let me try this red marker. Maybe it's a little better. Oh, so much nicer. What we're going to have to do here is we're going to have to move a wire, okay, or an area of wire through a magnetic field, or move the field, but of course what we do is we move the wire. Now the way that's done, actually done at a power plant, is, early in the last video we were saying you can do this, you can move the magnets, or make the magnets closer or farther, or move them around. It just doesn't work very well, and it's not very convenient to sit here and go flex the area out. Okay, of course you get big and pumped up. You do that, yeah, I get so pumped up, yeah, but that doesn't help. It's not very convenient. The convenient way of doing it, and the way it's done at power plants, is you need to take a wire and you rotate the wire between two strong magnetic fields. That's how you can induce a current. Okay, you got a flux change going on as that wire rotates. We're going to get a current moving through here. Now, the way it used to be done up to 20 years ago, just up to 20 years ago, was that you used to use gnomes. That's right, little short people. Yeah, get in there, turn that wire, you gnome. Oh, that's not very nice. I'm not getting paid enough for this. And the gnome would sit there and in between the two magnets and turn the thing. And of course, faster, faster, you gnome. As fast as I can go. And then along comes Hermione Granger, yeah, and she's all for gnomes' rights. Okay, we know what I'm talking about. Some of you know what I'm talking about anyways. We know. Yeah, Hermione, she comes along, and now the gnomes don't have to do this anymore. Nope. Just 20 years ago that happened. Yeah. No, seriously, look it up. Don't believe me. Then, how do they do it now? Well, it's all about boiling water. Yeah, that's what power plants do. They boil water. I thought they made power. They do, but in order to do that, you got to boil water. So, because boiling water makes steam, and steam, when directed into an ever-closing tube pipe, we all know from Bernoulli's, we remember Bernoulli's, don't we? Yeah, and steam is a fluid, and you decrease the area a fluid can flow through. It's got to go faster, and the steam comes out, and it hits a turbine, and a turbine is essentially a big fan blade, and that steam hits that turbine and spins that fan blade around, and then on that fan blade, what you have connected are some loops of wire, yes. And so our turbine, our fan blade, turns, rotating the wire, and we no longer need any gnomes. And Hermione is very happy. Okay? All right. Yeah. And so power plants, they have all kinds of ways you can boil water. You got to generate heat. So how can you do that? You can burn wood, you can burn coal, you can burn anything. You can burn trash, and you can, as long as you generate heat, burn oil. Nuclear, you can use nuclear, say it right, nuclear power, yeah, and that creates heat, boils water, makes steam, turns a turbine, rotates the wire in the magnetic fields. Now when that happens, we get our current induced. So what we want to know first is how much voltage, how much EMF, how much voltage we can produce by turning wires in a field. Okay, so what do we need to have? We have to have wires, and if we have N wires, that means the number of wires, a number of loops, I can say it, number of loops. So N means the number of loops. We usually just use an example of one loop, but if you increase the number of loops, you remember a solenoid. What happened, we did the electromagnetic thing, that sweet lab, yeah. And the more coils you have, the more effect you get. So if we increase the number of loops, we'll increase the amount of voltage we can generate. Okay, we'll usually just stick with one coil, but not always. So just be aware that N means the number of loops. And in this case, for example, I have one loop that's rotating. All right, then we have to have flux, phi, phi, fo, fum. That. Now we know that phi, phi, fo, fum is equal to flux, which is equal to, now you'll see it like that, I think, written in your AP handout. You can go check that, but I'm pretty sure it's written with the flux thing there. And then they give you what flux is equal to, so you make the substitution. So BA, we all know what BA stands for, bad. I didn't say it, okay. And I like to tell students, I rearrange these. They're all being multiplied, so it doesn't matter. And it's easy to remember. NAB, that word is easy to remember. NAB. Yeah, you got nabbed, okay? Yeah, we're trying to take this thing and he got nabbed by the cops. Yeah, that's easy to remember, nab. And so there's your flux. And there is a cosine of theta involved here with the flux. Remember that. But usually what you want to know is the maximum voltage. And so usually when you want to know just maximum voltage, this ends up being 1. Okay, the cosine of 0, remember the whole thing lining up the field with the perpendicular to the plane of the wire. Don't make me do it again, okay? I'm exhausted here. And that is usually going to give you maximum, that's usually 0, so that's 1. So usually, but I'll leave it in there, but usually we don't have to worry about it, but sometimes we do. So it is there. And then your change in time. And so you'll see this written as change in time, how long it takes for the event to happen. Things don't happen instantaneously. Things don't rotate instantaneously or move in and out of a field instantaneously. It takes some time to do that. I'll just usually write it as T. Okay, like that. T. But let me grab this over here and see. Here we go. Yada, yada, yada. I'm getting the thing. I'm getting your sheet. Oh, look, I tore that. I must have been once I was excited. Oh, so excited. And I get excited, I tear. So here we are, electricity and magnetism. Oops, excuse me, zip on down. Here we are. We're over here on we're almost done with this whole thing here, right? Look at electricity and magnetism. We're finally through all these equations, and now we're almost done. We're down here, and there it is. There it is right there. Okay, so yeah, on your handout, it's going to show you the flux equation, and then in the this equation here, it's just going to show it as I, and you're going to have to make that substitution in NAB. Remember NAB. Now, but they do put the delta in there. I don't put the delta in there. They also put the delta in for the flux. They put a delta here, and that just means that if you don't have any change in flux, you can't produce any voltage. Remember, the whole thing involves change, flux of the flux. You've got to keep changing the flux of the flux. So I did there. Yeah. So you've got to have a change in your flux in order to generate your voltage. And so we're talking about what we want to know is how much maximum voltage we can get. So hence going back to the cosine of 0, which is 1, and that's usually what you want to know. So there are deltas here. I just don't include them. Okay. And so there's your equation. All right, let's do a quick example of how to use it. Let's see, I'll read a problem out of the book, probably a homework problem, but I'll do it for you because you kids are my favorites. There we go, put that back. That goes here. All right, yeah, get that out of the way. Okay, I'm cleaning up here. Let's see, no problem in the book. I'll turn the page. Good song, Bob Seger. Bob Seger, turn the page, look it up. Great song, 70s. Number 5. Yeah, you have to number 5 as a homework. Okay, here's what it reads. I'll read it to you. A 12-centimeter diameter loop of wire is initially orientated perpendicular to a 1.5 Tesla magnetic field. The loop is rotated so the plane is parallel to the field direction in 2.2 seconds. Okay, so what we want to do is it's a loop of wire that's being rotated through our magnetic field. So a loop means that that's going to be a 1. So right now, with this problem anyways, not all, but this problem, we can get rid of this because there's only one loop. All right, sweet. Now what we want to know is the maximum amount of voltage that we can produce. If it's the maximum amount of voltage, I don't have to worry about this because maximum means that would be cosine of 0, which is 1. That's gone too. Oh, so easy. The area of the loop of wire times the strength of the field. The field was 1.5 Tesla, so I'll put that in there. The time of this rotation to get to maximum, going from minimum to maximum, that's what we want to know. This is the time it takes to go from minimum to maximum. The time it takes to get that maximum flux change. That's what this is. The time, I'm going to say it one more time, the time it takes to get the maximum flux change. Now that means that we went from 0 to maximum here in the rotated the plane is parallel to the field in 0.2 seconds. So 0.2 seconds. Okay, that goes here. And then here I need the area of the loop of wire. Sometimes it's a square, and if it's an area square is going to a rectangle, so you multiply the two sides together to get your area. But you all remember what the area of a circle is. 2 pi r. No, Billy, that's the circumference. 4/3 pi r cubed. Wait a minute, that's the sphere. That's right, Billy. At least you got that. I don't remember. Now, pi r squared, Billy. I was going to say it. Billy, he's angsty today. He always is. All right. Pi r squared. So pi r, radius, the diameter of the loop is 12 centimeters. So we want the radius. So 6 centimeters. But don't use centimeters. Use meters. So 0.06 meters and square that. And if I calculate this out, it'll give me the answer to how much voltage would be produced, the maximum amount of voltage that we produce while we're getting that rotation of the wire to go from a minimum to a maximum situation. So minimum is going to be 0 volts. Okay, you don't get any voltage produced. And maximum you get is the whatever that comes out to be. All right, so now, one more thing I want to talk about here is alternating current versus DC. Everything we've done up to this point has been direct current. Remember, direct current is just one direction. They're all so hot there, yeah. I like Liam. Okay, he's awesome. Now, not Liam in class, Liam, that, it's weird. Okay, moving on. All right, in one direction, him. Okay, so in direct current, you have the current going in, just in one way, one direction. But in alternating current, it switches back and forth, hence alternating. Why does it do that? We have to address why that happens. Now we can. Now we can determine why that happens. So imagine that this is my loop of wire, and I've got a magnet here and a magnet here. So I've got a magnetic field here. So I've got flux going through like this. So I'm producing a current. And then I go to minimum, okay, no flux. Okay, and then I go to maximum flux to minimum flux, maximum flux to minimum flux. What happens is, as I rotate through maximum flux, then, you get this effect where I get a current going through. So if I were to direct, so I got a north pole here out of the north, and I have my fingers going through here, and then I can go ahead and use that right-hand rule, okay, where I fingers, field, thumb in direction of the particles which are going to move, and then I can see what direction that's going to be. Now, once I rotate around like this, I still got my hand here, so remember it was coming out towards you like this, and now I rotate around through here, 0, back to here, maximum again. Now what happens is, remember the field's out of the north into the south. As I said, the north pole's over here, the field lines are going here. Now I grab the wire. Ooh, you should check that out, right? So grab the wire, okay, grab the wire. Now, once I've rotated 180 degrees, once I've done that, and now my finger is pointing out to you, remember? That's the way I hadn't moved that. So from here, my finger's pointing out. So the direction of the current is around this way toward you. Now, once I move around 180 degrees, the North Pole's still over here. Grab the wire. Okay. You see it. Okay, here. 180 degrees. Check it out. So the North Pole's here, goes through the loop. So I'll go ahead and grab that wire, and it shows the direction of the induced current. It's coming around like this, because that's toward you. Once we go 180 degrees, okay, remember it was going toward you. And then now we've taken the field is still going this way, out of north into south. And if I grab the wire, it's going away. It's going away now. It's changed, it's switched. So it switches directions. Okay, going this way. Okay, that's like up this way, and now it's going this way. It switches back. So boom, 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 boom. Every time it's rotating around, it's switching directions, hence the alternating. So we get a two-direction switch in a 360-degree sweep. So as the wire sweeps around, 180 switches directions, back again, 180 switches directions. One full rotation has two switches. Okay, so you get a back and forth, hence alternating current. So the current keeps shifting back and forth as we keep rotating the wire. So I can't do this fast enough. Okay, you need gnomes to do this. Okay, I can't do it. Ow! Oh, yeah. All right, but that's why you get the alternating current. As you rotate that wire through, you know, fingers feel, grab the wire, you can see the direction of your thumb is going to point in different directions. Okay. All right, so that's alternating current. That's why it alternates, because of the rotation of the wire and using our, you know, our right-hand rule there. Yeah, second right-hand rule. Okay, I think that's all I need to cover. This is getting a long video. I don't like long videos. I'm trying to keep these shorter now. Okay, faster uploads too. So, okay, I think that's it. I think we have the equation down. So now we can now use Faraday's law of electromagnetic induction for solving problems. Okay, kids.